Alright, let's start this problem here with a mass at the top of a hill, and let's say it has an initial velocity, and let's say that initial velocity is equal to, let's say, 10 meters per second. Now that mass is going to get to the bottom of the hill, and it's going to have some other velocity. Now this final velocity is going to be an unknown value. So the height that is between here, let's say that's going to be 60 meters between the bottom and the top. Our objective here is to find the final velocity. Okay? So how do we do this? Well, this is an initial energy equals final energy type of a problem. And hold on a second. Well, the initial energy is going to be mgh initial plus the initial kinetic energy, which is 1/2 mv squared. Oops, that's supposed to be an I. And that's going to equal the final position plus the final velocity. So you have here your initial gravitational potential energy, your initial kinetic energy is equal to your final gravitational potential plus your final kinetic. If you've noticed though, in this problem I have not provided the mass. So it doesn't really matter though, because whatever mass it is, all these masses are going to cancel out. So in fact you don't need it. We are looking for this variable as our final, so we can simply multiply everything by 2 to get rid of this 2 here on the bottom. So it ends up being 2gh I plus vi squared, and this term here completely disappears because h final is 0, so we can forget about it. Therefore, the only thing left on the right hand side of the equal sign is our final velocity. So if we take this up here and we continue, basically our final velocity is going to equal the square root of 2ghi plus vi squared. Now what's really interesting about this is we've come to this conclusion from energy, but interestingly enough, had we dropped a mass using our old kinematics equation, v final squared is equal to v initial squared plus 2a delta d, you'll notice that this is the exact same equation, because delta d corresponds to the original height. Okay? All that's left now is we need to plug in our values. So we can just go 2 times g times 60 meters plus my initial velocity, which was 10 meters per second, and then square that, and now all that's square rooted. So there's the solution to this problem, and what's really nice and interesting is that our kinematics provides the same solution as our energy problem, and the reason for that is because there's no frictional losses as it's sliding down. The energy method is actually more flexible, because if we did have an energy loss, we could, let's say for example friction, we could have added it here. We could have said, all right, how much work was lost to friction, and if we knew that value we could still find the answer as for the final velocity. So there's our first energy problem.